Hello students and welcome back. I believe we are on notes number 3 today. We are going to have a radical time. Hopefully we just finished doing kind of a card sort activity where we looked at some relationships between radicals and exponents, and we also looked at some definitions of imaginary numbers. So let's just jot down the important information in our notes. So the things that we had that related to radicals from the card sort activity are that the square root of n is equivalent to n to the 1/2 power. The cube root of n is equivalent to n to the 1/3 power. And we can generalize that and we can say the kth root of n is equivalent to n to the 1/k power. Okay, we can also combine exponents and radicals. So for example, the cube root of n squared is equivalent to n to the 2/3 power. And conversely, the square root of n cubed, notice I'm using the same two numbers but in different places, that would be equal to n to the 3/2 power. We also know that 1 over square root n is the same thing as n to the negative 1/2 power because reciprocals are negative exponents. We know that from our exponent rules. We also need to remember what conjugates are. Oops, let me see if I can spell it correctly. Conjugates. Conjugates are expressions that look very similar. Radical conjugates are expressions that look like this: a plus square root b and a minus square root b. Or it could even be like square root a plus square root b and square root a minus square root b. The point is one has plus, one has minus, and when we multiply them, we see that the radicals end up canceling out and all we have left is just a rational number. Okay, also we want to remember that the process that we call rationalizing a denominator is basically just a method for simplifying an expression that will eliminate the radical from the denominator. So we'll say that rationalizing a denominator is eliminating the radical from the denominator. And there's a process to do that, which would keep the expression to have the same value. We don't want to change the value of an expression. Okay, then related to imaginary numbers, the main ideas are that I is the imaginary unit and it's defined as the square root of -1, and I squared is defined as -1. So this allows us to talk about the square roots of negative numbers and not to just say that they don't exist, but we've defined them as imaginary. The standard form of a complex number is a plus bi, where a is the real part and bi is the imaginary part. A and b are both real numbers, but bi would be imaginary. And then we also have complex conjugates, so just like radical conjugates, which seems to be a really tough word for me to spell. There we go. Radical conjugates and complex conjugates both look alike except one with a plus, one with a minus. So we could say we have a plus bi and a minus bi. And when you multiply complex conjugates, the imaginary terms are going to end up canceling. Okay, next we're going to work through 8 different examples, and they each in their own way have something to do with radicals or complex or imaginary numbers. So number 1 is the square root of -98, and we're going to simplify it. So because it's the square root of a negative, this is an imaginary number, and anytime you're working with an imaginary number, the first thing you do is change it to its imaginary form. So remember that the square root of -98 is the square root of -1 times the square root of 98, and the square root of -1 is I. So the first thing we do is I times square root 98. From there, you can go ahead and simplify the square root of 98. So some of the steps I write, you might find you're doing in your head, and that's generally okay. Just kind of depends on how much you feel comfortable doing in your head. The square root of 98 can be broken down into the square root of 49 times the square root of 2. And we know the square root of 49 is 7, so we have 7i square root 2. We just write the 7 before the I because it looks better. We don't write I7, we write 7i. Just like if we had 7x, we wouldn't write x7, we would write 7x. Okay, so this expression has been simplified. Let's take a look at number 2. All right, so this expression looks like something you might come across if you were using the quadratic formula, for example. And so we want to make sure we can simplify this sort of thing accurately. So just like number 1, we see that we have the square root of a negative. So the first thing we want to do with that is go ahead and change it into its imaginary form. So we have 15 minus I square root 75 over 5. Now let's simplify the square root of 75. 75 is 25 times 3. You can write that down or you can just think that step in your head. And the square root of 25 is 5. So we have 15 minus 5i square root 3 all over 5. Okay, at this point I just want to caution you that this is where a lot of students make mistakes. When trying to reduce the expression, a lot of students reduce it incorrectly because they might reduce part of it and not the whole thing. So I'm going to give you a couple of different ideas for how to do it correctly. One way is to split it up into two fractions. So you would have 15/5 minus 5i square root 3 over 5, and then you can reduce each fraction separately. 15/5 reduces to 3, and then 5i square root 3 over 5 reduces to I square root 3. Another idea, going back to the previous step, would be to factor 5 out of the numerator. So if you factor 5 out of the numerator, you have 5 times the quantity, 3 minus I square root 3. And then you can cancel the 5 from the top and the bottom. And so you're left with 3 minus I square root 3. So you get the same answer either way, obviously. It's just a different way to think about it. Okay, let's move on to number 3. So when you look at the expression we have here, notice that you have complex conjugates. 9 minus 8i, 9 plus 8i. And when we multiply these together, just like you would multiply any binomials together, we're going to use the FOIL method. So multiply the firsts, and we have 81. Multiply the outsides, that's the O in FOIL, and we have plus 72i. Multiply the insides, that's the I in FOIL, and we have minus 72i. And multiply the last, that's the L in FOIL, and we have minus 64i squared. Okay, let's simplify this. So notice that we have plus 72i and minus 72i, so those add to 0. And this is going to happen every time you multiply complex conjugates. The inside and outside is going to just cancel because they add to 0. So in the future, you don't even need to write that part out. You know it's going to happen, so just do full and eliminate the oi. Okay, so that leaves us with 81 minus 64i squared, but don't forget that I squared is negative 1. So you always replace I squared with negative 1. So that means we have 81 plus 64, and that would give us 145. So you multiply complex conjugates and you just end up with a real number. All right, let's take a look at number 4. We have conjugates here too. They're not complex conjugates, they are radical conjugates. And if you multiply these using the FOIL technique, once again, first is 9, outside is minus 3 square root 2, inside is plus 3 square root 2, and last would be minus 2. Now would you look at that? Once again, the insides and outsides add to 0. We should have known that, right? We don't have to do the oi, we just do the full if you have conjugates. So because those outsides and insides cancel, all we have left is 9 minus 2, so that's just 7. Okay, let's see what's next. Rationalize a denominator. Okay, remember that rationalizing the denominator is changing how the expression looks without changing its value. It's like you change your clothes and you change how you look, but you still have the same value. So we want to change how it looks by making it so that it no longer has a radical in the denominator. Now, a lot of people might think, well, okay, I should multiply the top by square root 8 and the bottom by square root 8. Well, that's not wrong, because what you're doing is just multiplying by a special form of 1, right? That's just a big old 1. But if you use square root 8, it's actually not as efficient as you could be. So I'll show you what I would do instead. First, I would simplify the radical. Square root 8 is the same thing as 2 square root 2. Now the only thing we need to multiply the top and bottom by is the radical part, square root 2 over square root 2. So there's our special form of 1. This is my gigantic 1 right there. Okay, so now that we're multiplying by square root 2 over square root 2, multiply the numerators and we get 5 square root 2, and multiply the denominators. 2 times square root 2 times square root 2 is going to be 4. So this expression is now 5 square root 2 over 4. Remember, it has the same value as the original expression, it just looks different. Sometimes when you rationalize, it doesn't make things look any simpler, they just look different. And what you could do if you wanted to test out whether your work was correct is you could put this in the calculator, look at the decimal value, and put this in the calculator, look at the decimal value, and make sure they're the same. Okay, cruising right along, we're going to do number 6. So we're rationalizing this denominator, and this time instead of a square root, we have a cube root. So the same general principle applies. We don't want to have a radical in the denominator, but the process could be a little bit different. So I'm going to think of my cube root of 4 as the cube root of 2 squared, since 4 is 2 squared. Now ultimately, what I would like to see when I multiply by some special form of 1 here, what I would like to see is my denominators multiplying to give me just 2. So the cube root of 2 squared times the cube root of what would give me just 2. It would have to be the cube root of 2, because then altogether, when you multiply those denominators, you would have the cube root of 2 cubed. Now let's extend our thinking. What if you had the 4th root of 2 squared? Let's imagine this off to the side. If you had a denominator of the 4th root of 2 squared, what would you need to multiply it by so that your new denominator was just 2? You would need to multiply it by the 4th root of 2 squared, because you need the 4th root of 2 to the 4th. So you would need 4 2's under the radical if you're doing a 4th root, 5 2's under the radical if you're doing a 5th root, etc. So back to our problem. We're multiplying the denominator by cube root of 2, so we're going to multiply the numerator by cube root of 2 as well. So the numerator, when we multiply them, is 5 cube root 2, and the denominator is 2. Once again, to check your answer, you could put this in your calculator and put this in your calculator and make sure that they were the same. Okay, we have 2 more examples. Another denominator to rationalize, but this time we have an expression with a sum, and you could also have an expression with a difference. Either way, the same kind of process applies. It's not going to work out well if you just multiply the top and bottom by square root 5. Give it a try and see what happens. Remember, you would have to multiply by the whole denominator, so you're going to have to distribute. You're not going to get rid of your radical. So you need something else. We need to know what else we could multiply by 3 plus square root 5 that would end up with no radical. Do you realize what we're talking about here? I think you do. I think if we go back, remember conjugates, when you multiply them, you're not going to have a radical anymore, and we saw that happen on problem number 4. So what is the conjugate of 3 plus square root 5? That would be 3 minus square root 5. So we're going to multiply the numerator and denominator by 3 minus square root 5. That is our special form of 1. And remember, when you do that, you're going to multiply, distribute, FOIL, however you want to put it, multiply the whole thing. So for the numerator, I'm going to leave the 2 on the outside momentarily. And then for the denominator, I'm going to go ahead and multiply those conjugates. Remember, we don't have to FOIL, we just full because the OI is going to cancel. So we multiply the first, 3 times 3, we get 9, minus, multiply the last, square root 5 times square root 5 is 5. So the denominator is 4. Okay, now do you see why I left the 2 out there momentarily and I didn't multiply it through? It's because I was anticipating that there is a chance that the 2 would reduce with something on the bottom. And indeed it does. So we can just do that. And we have 3 minus square root 5 over 2. Is there anything better about this expression compared to the original? Is it better? Does it have a different value? No, it just looks different. Remember, same value, different looking expression. You could put that whole expression in your calculator. You could put that whole expression in your calculator. You would get the same thing. Okay, let's do the last one. Okay, this problem takes the place of division of complex numbers. So it's basically just looking like a fraction, but this instead could be thought of as complex number division. We don't really have division. We have addition, subtraction, and multiplication. But what we want to do is we want to end up with an expression of the form a plus bi, because that is standard form. So either a plus bi, a minus bi, it doesn't matter, but we just want the real part plus or minus the imaginary part. So the problem right now is we have too complicated of a denominator. And what can we multiply by to simplify the denominator so it no longer has I in it? That's right, I hear you. You're telling me use the conjugate. So I'm going to multiply by the conjugate of the denominator, 3 minus I. Multiply by that over itself because we have to use a special form of 1. Make sure we FOIL. So when we FOIL the numerators, when we multiply it out, we have 15 for the first, minus 5i for the outside, minus 15i for the inside, and plus 5i squared for the last. And then for the bottom, because they are conjugates, we just full, we don't OI, because we know the inside and outsides are going to cancel. So we get 9 minus I squared for the first and the last. I'm going to drag this over here to finish. I think there's going to be a few more steps. So what we want to do is replace every I squared with -1, and we want to combine our like terms. So we have 15 minus 20i plus 5 times -1 over 9 minus -1. Okay, we know that 5 times -1 is -5. 15 and -5 is 10. So we have 10 minus 20i, and then on the bottom we have over 10. So let's break this up. 10 over 10 minus 20 over 10 times I, and we just have 1 minus 2i. And 1 minus 2i is in standard form. Ta-da! Okay, so all that we have left then is today's assignment. So we have some problems that have to do with radicals and some problems that have to do with complex and imaginary numbers. And remember, the ones with the hearts around them are the ones that have tutorial videos available. So if you get stuck on any of those, you can go ahead and check out those videos. And I just want to remind you to upload your notes as well as your assignment and show evidence that you have checked your work. And always come back and see me if you have questions that you don't want to save for the next day. Thanks, everybody. Have a wonderful day.